Hello again. So this represents a so-called optional section in my revised schedule. So what that means is I'll not assess this knowledge in any way. On the other hand, it's an important knowledge to have in terms of understanding the content of the class pre-calculus. So with that said, let's go ahead and get started. So we've already established some algebraic techniques that help us solve exponential and logarithmic functions. We've seen that some such functions model important things. We've seen like radioactive decay. We've seen a little bit of population growth. There's going to be more population growth today. We'll also talk about interest rates and return on investment, perhaps bland as that seems. So let's go ahead and get started. Population first. So if you have some population which lives in an environment without any limiting factors, there's unlimited food, there's no predators eating them, there's not a cap on the amount of space they have, they can spread out all they want, then the population will grow exponentially. So clearly there's no such environment, and as the population balloons to be big enough that it runs into some limiting factors, the growth will stop being exponential. So let's go ahead and try to understand that. So if you start with some initial population p0, then the population at time t will be given by the initial population times some exponential function, so some function of the form e to the kt, where k is some constant. So let's talk about units. P of t is the amount of population, and depending on what you're talking about, the units, different sorts of units might be appropriate. If you're talking about a population of elk, then probably you're measuring it in number of elk as individuals. Possibly, units are actually like thousands of elk, which is also fine. If you're measuring a population of bacteria, a sample of bacteria, you probably don't want to say there are this many individual bacteria. Instead, you're just going to say something like, what is the mass of the sample of bacteria? T is measured in time. Could be hours, could be seconds, could be years. It doesn't make sense for the thing in the exponent, namely this thing, to have a unit next to it. I don't know what e to the 5 seconds is. So that constant has some unit next to it that must cancel out the unit coming from the time. So k will have a unit of the form 1 per hour or 1 per second next to it. So let's try to understand this. So let's suppose you have a population of bacteria growing in a petri dish. The initial population, the initial sample of bacteria, consists of 0.2 milligrams of bacteria. You wait 1 hour, you now have 0.3 milligrams of bacteria. How long will it be until you have 1 milligram? Well, this population is growing exponentially. This petri dish is a very rich environment without any limited amount of food for the bacteria to nibble on. So we'll start by determining the constants. So P0 is the initial population. And that is, in this case, given right here, 0.2 milligrams. We're also given the population at some time. At time equals 1 hour, I'm given that the population is 0.3 milligrams. So that means the population at 1 hour, so I'll plug in t equals 1 hour to the formula, will return 0.3 milligrams, and I have a formula for the population at any given time. It's this. I know what P0 is. P0 is 0.2. 0.2 milligrams times e to the k, a constant that I don't know, times the amount of time that took, 1 hour. Does that look like the type of equation we might be able to solve for k? I think so. Let's try to solve that for k. So the first thing to notice is it looks like both sides have a milligram next to it. That's good. So those units will just cancel. And maybe I'll even jump another step deep. So the first thing that I'm going to do is I'm going to divide this to the other side. So I'll wind up with 0.3 milligrams divided by 0.2 milligrams is equal to, and now all the other stuff that was on that side that I didn't multiply over yet, e to the k times 1 hour. All right, and as I said, those will cancel. And it looks like the thing on the left-hand side, in fact, simplifies. They're both 0 point something, so that's just 3 halves. No need to be fancy about it. You could write it as 1.5 if you wanted to. Nice. So now I see that this is equal to that. That is an exponential equation. I can simplify it. Simplify in the sense of I'll have k closer to just being on its own by rewriting in log form. And this is an exponential with base e, so I should take log base e, also known as natural log of 3 over 2, is equal to k times 1 hour. Well, I can solve that for k, right? Just divide the 1 hour over to the other side. So ln of 3 over 2 times 1 over 1 hour is equal to k. And this is one of the reasons that I kept track of the units, is if you look at this quantity, it does have a unit. The unit is 1 per hour. So exactly the type of units that we expect to see on that constant. Let's use this model to make a prediction. And what was the prediction we wanted to see? We wanted to see how long it would be before there is 1 milligram. So we have a formula now. I've just computed k. So I figured out what the k is in the formula. I know the initial population. The initial population is 0.2 milligrams. I know the target population size. The target population size is 1 milligram. I should be able to solve for t then. Let's solve for t. So right here is the eventual population, so that's p of t. Now I'll write down the formula for p of t. That is p0, 0.02 milligrams, times e to the k, ln of 3 over 2. And maybe I'll suppress the units. No, I won't yet. Times 1 over 1 hour times t. There's the equation that I have to solve. And well, I see what I have to do. I'll start by dividing this to the other side. If I do that, I'll start right here. E to the ln of 3 over 2 times 1 over 1 hour times t is equal to 1 milligram divided by, oh, I miscopied that. Should be 0.2 milligrams, right? Not 0.02. Divided by 0.2 milligrams. And just as before, the milligrams cancel. Well, you can do the division on your own, but maybe I'll say this. 0.02 is the same thing as 1/5, so that's 1 over 1/5. That's 5. Nice. So now, what do I see? I see an exponential function, something exponential looking, is equal to a number. Well, that's exactly the type of thing that you should rewrite in logarithmic form, like so. So I'll end up with ln of 3 over 2 times 1 per hour times t, the thing I would like to know, is equal to the log base e, the natural log, of 5. Nice. Well, this looks like it's super easy to solve for t. I just need to divide this to the other side and multiply by hours. So, doing that, I'll get t equals ln of 5 divided by ln of 3 over 2 hours. And since this is a vaguely applied problem, I would probably like to know how big that is. So t, this value for time that we found, is approximately, and let's see, there, I'll give myself space there so that I can, as per usual, do the computation. You don't need to see me doing the computation in that you'll do it faster than I can anyway. All right, and there we go. The natural log of 5 divided by the natural log of 3 over 2. Oh, I wanted it to scroll inside of the window. There we go. And that is somewhere around 3.97. .97 hours. Very nice. Let's do a quick follow-up. So it takes 4 hours to get up to 1 milligram. Let's see how large the population is at t equals 1 day. Well, so notice this isn't me trying to solve for t. T is given. T is given. I just need to use the formula. I want to compute population when time equals 24 hours. So that just means I need to plug in t equals 24 hours to the given formula. And, well, the formula is way up here. But I still know P0. P0 is 0.2 milligrams. Times the natural base for an exponential raised to the power k, ln of 3 over 2 times 1 over 1 hour. So all of this is k, times the amount of time we're allowing to pass, which is 24 hours. And, well, again, we can do a little bit of simplification. Those hours will cancel. There's a unit of milligrams, so I'll just remember that when I go and use a computer to make this computation right now. Doing that. All right, carrying on. So let's just see what I've done. 0.2. I've dropped the milligrams. I just need to remember I need milligrams in there. E raised to the ln of 3.2 times 24. There it is in pretty print, exactly as I need. Now, there could be a little bit of simplification done, but I didn't. The resulting thing seems to be around 3,400 milligrams. Also known as 3.4 grams. Maybe I should keep reminding myself that this is approximate. So, it looks like after 24 hours there will be 3.4 grams of bacteria, which is a pretty big number. And so you notice that if I say waited another day, it would grow exponentially by the same factor, so there would be even more of it. In fact, let's go ahead and do that. I'm not going to go aside for this. So if I waited another day, I would wind up with a number times 10 to the 7th. So it would be on the order of 1,000 is 10 to the third, so 10 million, 50 million milligrams. So that would be a lot of bacteria, and it's unreasonable to expect that to live in the same petri dish. So our remark here is, what we're seeing is, eventually, the population will reach some sort of limit and stop growing exponentially. So you'll notice that while in this example we were using a base of e, and there's no need to use a base of e. We can use any base we want. So an alternate formula, the population can which grows exponentially is also given by p of t equal to initial population times any base raised to the t, where there's that base. It should be a positive number, and maybe this t should be divided by, I don't know, some unit of time, hours, because I don't know what b to the 5 hours means. I know what b to the 5th is, but not b to the 5 hours. To see that these are the same things, it's just a matter of using some exponential laws. So p0 times e to the lambda t, that's the same thing as p0 times e to the lambda to the t, is it not? Right, e to the lambda to the t is e to the lambda t. This is a constant. There's the b. Sometimes the numbers just walk out better with a careful choice of b as opposed to trying to walk it out this way. So let's do this. So let's suppose you start with a population of 3 rabbits. You wait 4 days, you come back to find 8 rabbits. So this is obviously a ridiculous example. Rabbits don't actually reproduce that quickly, but these are make-believe rabbits. How many rabbits do you expect to see at day 10, given that they're growing exponentially? So step 1, determine all the constants. So the initial population is 3 rabbits. At time equals 3, there's a population of 8 rabbits. So that means 8 is equal to, I have a formula to use, this formula. 8 is equal to the initial population times the unknown base b raised to the t, which is 4. Oh, hey, does that look like it's easy to solve for b? Sure does. So I guess that I'll divide by 3 to get 8 over 3 is equal to b to the power 4. So I need to undo raising b to the power 4. I guess that means I need to take the 4th root. So b is equal to, well, maybe I won't even say the 4th root. That's 8 over 3 raised to the power 1 over 4. And you might be tempted to get a decimal approximation, but I'll go ahead and say that you shouldn't get a decimal approximation because I'm not done with the problem. If you get a decimal approximation now, you're inviting propagation of rounding errors. So I'll leave that b alone. I have a formula for what b is. I can use that to make a prediction. So let's actually address the problem. I want to know what the population is at day 10. So that means, apparently, I want to plug in t equals 10 days, but I'm being consistent with my unit, so I don't need to worry. So let's use the formula above. Population at time equals 10 is equal to p0, which is still the same as it ever was. It's still 3, times b, which is 8 over 3 raised to the power 1 over 4, It looks complicated, but don't worry, it's fine. I need to take that and raise it to the 10th power. We can do some simplification now. That's 3 times. So I see a base raised to an exponent raised to an exponent. So I should just multiply those exponents. So 3 multiplied by 8 over 3 raised to the 10 over 4. Well, 10 over 4 is the same thing as 5 over 2. And notice that 5 over 2 is only in the exponent of 8 over 3. That 3 is just on its own. So again, if we wanted to actually approximate this, which let's say we do, I certainly didn't specify that I wanted a decimal approximation as opposed to an exact answer, but we have the ability to get both. This is an exact answer. Let's get a decimal approximation. Okay, and we're back. I've asked a machine to do the computation. Let's see if I've typed it correctly. I wanted 3 to the 3 raised to the power 8 over 3 raised to the power 5 over 2. 3 times 8 over 3 raised to the 5 over 2. There it is in pretty point, which helps gauge if you've actually entered it correctly. So I wanted only 8 over 3 to be exponentiated, so I needed those parentheses. And I wanted all of 5 over 2 to be in the exponential, so I needed those parentheses. And let's see what the result was. Around 35 rabbits. So population at time 10 is approximately 35, and well, let's give more digits. 34.9 rabbits. And there's one thing that you'll notice. This is not a whole number of rabbits. This is a decimal number of rabbits, which you might object to, saying that doesn't make sense. But we're just accepting that this is an approximate model. So it's predicting if the growth of the population of rabbits were truly exponential and continuous, which it kind of isn't, right? There's a single moment when an individual is born. It would predict a population of 35 rabbits, which is also absurdly big. But that was built into the fact that the problem was stated absurdly. Right? A population of rabbits going from 3 to 8 in the course of 3 days is excessive. No. That should have been a 4. But I think that was fine. That was consistent throughout. Nice. So I'm going to stop this recording here. I'm going to stop this recording here. And the next video posted will be about interest rates and the way they're computed, with the goal towards saying that if you want to understand continuously compounded interest rates, you need the natural exponential. It's just the thing that pops up. Great. I'll see you in a moment.